Hey friends! With this short video, we're going to do an introduction to one of my favorite units, exponential functions. So what you have on this slide is two exponential functions with their graphs, and an exponential function is any function where we see the variable in the exponent. Oh, that's not a highlighter. So in this equation, our x is in the exponent of 2, or we've got 2 to the negative x, and these graphs have some pretty similar features. We can see that as we go in one direction, our graph is starting to flatten out, and as we follow that graph into the other direction, it's getting steeper and steeper and steeper and steeper. So that's going to be the general shape of our exponential graphs always, and we're going to talk a little bit more about why. Let's look at the same example, but let's look at it a little bit closer. So if we were going to make a table for this graph, let's start where x equals 0. If x equals 0, we're doing 2 to the 0 power. And any equation to the 0 power, any number to the 0 power, is always going to equal 1. So our graph is going to cross the y-axis at the point 0, 1. And then as we start to go up, as x equals 1, 2, 3, 4, well, 2 to the first is just 2. And then when x is 2, we've got 2 squared. 2 squared is 4. 2 to the third means 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. And then 2 to the fourth, 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. And as we do that math, we can see a pattern emerging to our y values as x goes up. We've got 1, 2, 4, 8, 16. We're not adding the same amount every time like we do with a linear function. Instead, we're multiplying by an amount. We're multiplying times 2, times 2, times 2, times 2 to find the values of our table. And this is called a ratio of change. So exponential graphs have a ratio of change. They follow a pattern of multiplication. And that means that they grow very, very quickly because, sure, as we're down here, we're going 1, 2, 4, 8, 16, but very rapidly we go 32, 64, 128, 256, 512, and we start to get much, much bigger, which is why it looks like our graph is getting steeper and steeper and steeper as we move to the right. So that's as x gets bigger, but let's look at what happens as x gets smaller. So once we start once we start plugging in negative values for an exponent, we get into fractional values because a number to a negative exponent is equal to 1 over the number to that positive exponent. So 2 to the negative second power is actually the same as 1 over, that's equal to 1 over 2 to the positive second power. And we already said what 2 to the second is. We said that that's 4. So 2 to the negative second is actually just going to be 1 over 4. 1 over 4. Smart Notebook doesn't type fractions very well, so bear with me. Yeah, and that sure doesn't look right. Close enough. You guys know what I mean. And that's my cat in the background. Similarly, 2 to the negative first would give us 1 over 2 to the first. So we'll have a value of 1/2. And if you look, our pattern is actually continuing into the negatives. We still have this ratio of change because a fourth times 2 is a half times 2 is 1 times 2 is 4, or 1 times 2 is 2. So those fractions fit right into the pattern. But as we move further and further to the left, as we get to 2 to the negative 7th, just like we got bigger and bigger and bigger very rapidly, moving to the right, now we're putting that bigger and bigger number on the bottom of a fraction. Well, 2 to the negative 7th is 1 over 2 to the 7th is 1 over a massive number. So we're getting very, very close to 0 very quickly. But we're never actually going to hit 0, right? There is no number that you can divide 1 by that will get you all the way to 0. We're just going to get smaller and smaller fractions forever until, as we get to 2 to the negative 8th, and then 2 to the negative 12th, and then 2 to the negative 100th, we're getting so close to 0 that we can't really even see the difference. So this line that we're kind of creating right here, along the x-axis in this case, is called an asymptote. And an asymptote is a line that the graph gets closer and closer and closer to, in this case 0, but it never can actually hit it. All right, so let's look at one more example. This one is going to be a region problem. In this case, we're graphing the function f of x equals 2 to the x minus 7 on the set of axes below. So right away, I can see that this is an exponential function because I have this 2 to the x power. And by coincidence, or because it's easier to see, we've done all 2 to the x, but that doesn't mean every exponential function has to be 2 to the x. We can have 3 to the x, or 4 to the x, or negative 12 to the x. But this one's 2 to the x minus 7, and despite that minus 7, it's still exponential. The variable is still in the exponent. So if I'm going to graph this, the first thing that I'm always going to do on the region is put that equation into y1 equals on my calculator, maybe take a quick look at the graph just to see the general shape of it, and then if I have to graph it, I'm going to go straight into the table, because the easiest way to graph anything is to plot 5 or 6 of the points and then connect them, right? That's how you're going to know that you have an accurate graph. So as we look at this table is not approaching 0 like our other one, but it is still approaching a number. It does still have an asymptote as we move into the negative x values. And so if we think about what we said before, as x is getting to be negative, and as it's getting to these larger negative values, this 2 to the x portion of it is getting very, very close to 0. But we're then subtracting 7. So as we get very, very close to 0 and then do minus 7, well, 0 minus 7 is negative 7. So we're getting very, very close to negative 7. So we're going to have an asymptote at y equals negative 7. And we can sort of see that happening in the table here. And if you're looking on your TI-84, you can keep scrolling, and you're going to see that this, as x gets more and more negative, this number on the right, this y value, gets closer and closer and closer to negative 7, but it never actually hits it. So we're going to draw in an asymptote at y equals negative 7, which is going to be a horizontal line at negative 7. But before we can do that, we better think about the scale of our graph, because right now, this graph is just blank, and the region loves to do that to you. So let's think about the scale, and in order to think about the scale, we're going to want to think about what x values we want to graph. So if we look at these smaller x values, we can see that we're starting with fairly small numbers. We're getting closer and closer to negative 7, and then we're going negative 6, negative 5, negative 3, 1, 9, 25. So y is growing very quickly, right? It starts out slow and then gets bigger and bigger and bigger. And if you're on your TI-84, you can scroll and see that it gets big very, very rapidly. So in order to fit a reasonable portion of our graph onto here, it doesn't really make sense to just scale y as 1, because if we're scaling it as 1, let me draw in a couple points here. Well, we'd say, all right, when x is 1, y is -5, 3, 4, 5. When x is 2, -3. When x is 3, 1. When x is 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'd only have this portion of the graph before we went all the way off. So it would look something like, pardon my handwriting, that, and we'd be wasting this whole portion of the graph. So instead, we're going to scale this a little bit differently. Let's make y a little bit bigger, and let's try to fit at least that 25 on. So I've got 10 boxes. I want to fit to 25. But I also want to make sure that I can see pretty clearly that we've got these -6, -5, -3, 1 values. So I don't want to make y go up by anything huge, because I want to be able to see the difference between -3 and -5 on my graph. So I'm not going to scale y up by tens or hundreds or anything huge like that. Let's start by just scaling it up by, 2. That'll get us a little bit further, right? If we scale it up by 2 in each of these boxes, and we've got 10 boxes up and 10 boxes down, each time we go up, we're going to go up by 2. We're going to get to 20. We're going to get a little closer to 25, but let's scale by 3. Then we'll get to 30. That sound reasonable? Then on the same note, with the x values, I don't really want to get all the way up to x equals 10, because by the time I get to x equals 10, if you scroll down the graph in your or the table in your T84, you're going to see that x gets absolutely massive. So instead, let's say that I'd rather graph from -5 to 5. I'm going to make x go up by 1 every 2 boxes. So my scale is now going to be something like 1, and let's just make that a lot smaller. 1, 2, 3, 4, 5, and it's going to move like that. And then from my y-axis, we said 3, right? So we'll go 3, and it would go 6, 9, 12, 15, 18, all the way up to 30. And I'm only marking every other line just because I want it to fit, and also I don't want to waste your time playing with making this look neat in Smart Notebook. So I think that you're hopefully getting the concept just from the few numbers that I've put up here, and on your paper, feel free to mark every box so that you can see exactly what's happening. All right, so now that we've decided on this scale, I do want to draw in that asymptote that we said we had at y equals -7. So if we're moving up by 3s, then this first box is -3 below 0, and then -6. And then that means that y equals -7 is going to happen in between -6 and -9, but definitely a lot closer to -6 than to -9. So let's make sure that we're being reasonably accurate about where we draw our lines in between. If we're scaling like this, I need to be about a third of the way down, so maybe even just a little bit. Well, a little bit closer. That's not bad. So we've got an asymptote at y equals -7. So then let's start to plot some of the points that we've got from this table. As we're over where x equals -5, we are very, very close to that asymptote, and we're staying pretty close to that asymptote through -5, -4, -3, -5, -4, -3. And we almost can't even accurately graph that difference because we're getting so close to -7 that it's really hard to eyeball. So we're just going to know that that's an asymptote and that we're getting fractionally closer to it. And then as we get up to -1, we're getting a little further away. We're getting up to -6.5, so I'm going to try to move just a tiny bit further down or further up. And then as we get to 0, we finally hit that -6. So I'm at 0, -6, then I'm at 1, -5, 2, -3, and now I'm back on the line. Oops. So we got a point there. And then we go 3, 1, 4, 9, 5, and we're all the way up at 25. And that becomes enough points that I can reasonably connect them and have the shape of my exponential graph. And you're going to have to pardon my handwriting as I do this on my laptop because it's going to be a lot wavier than it should be. But we're going to have that general shape where our graph flattens out as we move to the left and then gets steeper and steeper and steeper, moving to the right.